So we've got a solid of revolution problem where we've got the graph and we're going to be rotating this graph that's bounded between x and x cubed about the line y equal to 2. Okay, so whenever I do, looks like this is going to be a washer method. When I do washers, I think disk perpendicular. Okay, so my rectangles here are going to be perpendicular to the axis that you're rotating about. So I'm going to have a dx going on here. So if I think back to my formula for the volume of the shape, this is pi a to b of the big radius squared minus the small radius squared dx. So I need to figure out what the individual pieces are here. Okay, and once I do that, I can integrate it and apply the fundamental theorem of calculus, f of b minus f of a. So first thing that I do is I figure out where are my bounds starting and stopping. So I'm going to be adding rectangles from, well, it looks like 0 up to probably 1. But how do we check this? How do we do a bit better than looking? To find these intersections here, I set the two equations equal to each other. So x cubed equals x. Subtract x from both sides. I get x cubed minus x. Factor an x out. I have x squared minus 1 times x. And so x squared minus 1 is a difference of squares. So x minus 1, x plus 1. And so this gets me x equals 0, x equal 1, and x equal negative 1 are solutions. So if you kept drawing this out, it would actually cross again here too, but we're not worried about that one over there. But as we thought, this would be x equals 0, and this would be x equal 1 going there. So we drew the picture okay. Okay, so I'll make this a little bit smaller. All right. Now, the next thing that I need to do, since I've got the bounds from 0 to 1, I'm adding up all the rectangles between 0 and 1. Next thing I want to do is figure out what the big R squared is. Okay, so what is the big radius? Well, the big radius is the distance from the perpendicular distance from the axis we rotate about to the curve. So that distance, remember, to find distance, what do? I do top minus bottom. So the top minus the bottom there, what is the top? Well, that capital R of x, the top line is, well, I have a y equal to 2, right? And the bottom here, that bottom, so remember this is the big R, that's the little r, okay? So the most outside radius is, looks like that's the y equal x cubed one. So top minus bottom is 2 minus x cubed. So I'm going to do 2 minus x cubed inside my first one here. Okay. And then the next one, the little radius. So the little radius is the distance from the axis we're revolving about. So we're revolving about y equal to 2. To the inside radius, so that right there. So that's, once again, that's y equal to 2 down to y equal to x. So the little r of x is equal to top minus bottom, which is equal to 2 minus x. So I do 2 minus x in here, close parentheses, square it, dx. Okay? So now I do some algebra and I get an answer, and we can walk through that. 2 minus x cubed times 2 minus x cubed. This is 4 minus 4x cubed plus x to the 6th. And then 2 minus x times 2 minus x is 4 minus 4x plus x squared. Combine all these together. Remember, it's pi integral 0 to 1 parentheses 4 minus x 4x cubed plus x to the 6th, and then right here dx. And so if I simplify, I get pi integral from 0 to 1. Now the 4's, it looks like those 4's cancel. I get a positive 4x minus x squared minus 4x cubed plus x to the 6th dx. If I integrate these pieces, I get, well, what is that? 2x squared minus x cubed over 3 minus x to the 4th, and then plus x to the 7 over 7, just using the integration power rule. Okay, add 1 to it, add 1 to the exponent, divide by the exponent with the 1 added to it, evaluated from 0 to 1. And so whenever I plug in, I have pi, and I have 2 times 1 squared is 2, minus 1 cubed over 3, minus 1 to the 4th, plus 1 to the 7th over 7, and then minus pi times, and all those pieces go to 0 whenever I plug 0 in. And so when I simplify here, I get pi, and then let's see, 2 minus 1, that gets me 1. And I'm going to go ahead and rewrite this as 7 over 21 and plus 3 over 21. And so that means this is 21 over 21. And whenever I combine all those, get 17 pi over 21, okay? Which is approximately 2.543. So if I want the exact answer, this is what I'm looking for. If I want an approximation, then that's what I'm looking for there, okay? But what I'm really going for in the grade is, can you set up this integral right here? This is really what I want to do. And then the algebra is nice, integrating it is something that I'll look for, and then the final answer is just one part of multiple things that I'm looking for in all of this setup, okay? So we got one more problem. And this one here, instead of rotating it about a horizontal line, we're going to rotate it about a vertical line. And so this vertical line here, x equal to 2, we're going to rotate this shape. Now, one thing that I didn't do with the last problem is draw the 3D picture. I'm going to draw the 3D picture here, and just so you know, the picture is really close. I mean, it's not the exact same, but it's very similar to the same shape, okay? Well, let me try this again. So inside it kind of bends in like this, so it's got a little bit of a thickness. Not much. So it's like a hollowed out volcano here. All right. So let's get that little thickness going on there. And then, you can see clearly in the middle, it's just kind of hollowed out. Okay. So, what I want to do is I want to take a cross section. So I'm going to take one cross section through it. And then whenever I take that cross section through it, I realize that it is hollow in the middle. So what does that tell me? That tells me I'm dealing with that washer method. Okay, so I'm dealing with the washer method. Okay. Remember, your rectangles are always perpendicular. So this is a dy cut here. Okay. So what do I need to do with the dy cut going on? The volume is equal to integral from c to d of pi, and then capital R of y, a function of y squared, minus little r of y, the little radius, squared, dy. Okay? So I'm integrating with respect to y with my dy slices here. I need to figure out what the big radius is first. Okay? So how do I get the big radius? So the big radius, also known as the outside radius, this is the distance. This is the distance from the axis we're rotating about to the outside layer. So the outside layer here is that straight line looking thing, y equal x. So that distance, remember to get this, it's right minus left. Okay, so the rightmost one is x equal to 2. Okay, and then minus the left, that's a y equal to x. And so remember, we write it as x equals something, right? So what am I doing? I'm doing right minus left. So this becomes 2 minus y. So I've got pi, and then the integral c to d of 2 minus y squared minus, and now I need to figure out what the little radius is and square it. I also need to figure out the bounds on the integral. So where am I summing my rectangles from? Well, my rectangles start where? At y equal looks like 0, and I sum them up to looks like 1. But to check this, I set the equations equal to each other. X equals x cubed. This is the same problem as earlier. We found that x equals 1, -1, and 0. So once again, that will tell me if x equals 0, then y is equal to 0 here. And if x equals 1, then y is equal to 1 here. Okay? And if you look at the graph, it definitely looks like it lines up like that as well. All right, so I'm integrating from 0 to 1. I'm adding all those rectangles from 0 up to 1. All right, so little radius. How do I find the little radius? Well, the little radius is the distance from the axis we're rotating to over to the shorter radius, little r right there. That was little r, this was big R, right? So the little radius, r of y, right minus left is still 2 minus the left. Well, the left ends up being x cubed. So 2 minus x cubed. But what's the problem with what I've written here? I have an x in here, but this is with respect to y. So how do I fix this? How do I make this in terms of y? Well, if I have y equals x cubed, then to get x equals something, I take the cube root of both sides. So x equals the cube root of y. So now I'm going to replace this x cubed here with the cube root of y. All right, so if you ever get to this point in your process and you've got the wrong variable, it doesn't match up with your differential, right? And you know what your differential is if you draw the picture and do the arbitrary rectangle like you're supposed to, that's perpendicular to the axis you rotate around, then you would know, you got to figure out a way to rewrite that in terms of the proper variable. So x here is equal to this cube root of y. Okay? So I can do some algebra simplification. 2 minus y squared is equal to 2 minus y times 2 minus y, which is 4 minus 4y plus y squared. And then 2 minus the cube root of y times 2 minus the cube root of y is 4 minus 4 cube root of y. And then this one might be tricky to you, but this is plus the cube root of y squared. Okay, if you multiply the cube root of y times the cube root of y, how many y's do you have? You got 2 y's inside, right? And so that's where that cube root of y squared comes into play. Okay? So take this, do your algebra simplification. So I have pi integral 0 to 1. Looks like the 4's are going to cancel. And so I have minus 4y plus y squared plus 4 cube root of y plus cube root of y squared dy. Now what I'm going to do is I'm going to rewrite this in terms of rational exponents so I can use the power rule to get this. Now remember, if I have the cube root of y, it's understood that there's only one y there. Rational exponent says the horsey goes outside and the rider goes in the house. But when you're riding, the rider goes on top and the horsey goes underneath. Okay, so the rider is on top and the horsey is underneath. Okay, the rider is on top and the horsey is underneath. The rider is in the house, the rider's on top. Okay, so that means that this is y to the 1/3 and then plus y to the, try this one out, see if you can do it. Yep, it's 2/3. Okay, dy. Ooh, I wrote dx here, sorry about that. That should be dy. Okay, now whenever I integrate, I'm going to add 1 to the exponent, so minus 2y squared. That's what happens there. You can go through the math to check that. Okay. Then plus y cubed over 3 plus, well, if I add 1 to 1/3, I get 4 over 3. But then whenever I divide by 4 over 3, what happens? The 4's cancel, and so I end up getting 3. Okay, and then plus, and then add 1 to 2/3. What do you get? You get, that would be 5 over 3. And then dividing by 5 over 3 is the same as multiplying by 3 over 5. So don't do this in your head like I just did. Do it, write it out if you're not comfortable doing that, okay? And so when you type in 1, you're going to get -2 plus 1/3 plus 3 plus 3/5. And when you plug in 0, you just get 0 for all those. Okay, so that whole thing goes to 0. And so when you collect like terms here, you end up getting 11 pi over 15, okay, which is approximately 2.304. So hopefully this video helps you understand better how to do the disk and washer method. The disk method is just applied twice to get the washer method. You find the outside radius disk, and then what do? You subtract away the inside radius disk. And when you subtract that away, what you have left is the washer. All right, so it's literally you're just doing the disk method twice to get the volume of the washer. All right, so no big deal. Just going through the steps. The hardest part is finding that distance, okay? And when it's a dy, you're doing right minus left to get the outside and inside radius. When it's a dx problem, you're doing top minus bottom for the outside, and then top minus inside bottom for the inside there for the smaller radius. Okay, so always do perpendicular, okay, with the disk or washer method. You're perpendicular to the axis that you're rotating about.